But I'd like to introduce our speaker today, who's Kaitlin Loftus. So Kaitlin is a new Columbia postdoc through the NSF LEAP Science and Technology Center. She's working here at GISS with Marcus Van Leeuwenhoek on liquid cloud microphysics parameterizations. Kate recently finished her PhD at Harvard in the Earth and Planetary Sciences Department, where she studied the water cycle on exoplanets, solar system bodies through time, and modern Earth. So with that, I will hand things over to Kate.
Okay, awesome. Thanks, Maggie. As Maggie said, my name is Kate Loftus. I'm a new Columbia postdoc sitting at GISS. I have my office number somewhere. I think it's 668, maybe on the last slide. Yeah, and today I'm going to talk about how clouds make rain from a microphysical perspective. And this is going to span not only clouds on modern Earth, but also kind of generalized planetary atmospheres. So to kind of motivate this work, I want to start from a very simplified water cycle. Maybe I'll just move this. Okay, perfect. Yeah, so start from a very simplified water cycle, kind of centered around clouds. We can kind of think about three main reservoirs for water. So the first being kind of the surface, either kind of liquid or solid. The second being kind of gaseous water vapor in the atmosphere. And the third kind of being water in the atmosphere that's either liquid or solid phase, what we kind of think about as clouds. And the details of how water is kind of circulating between these reservoirs and kind of the temporal and spatial and phase distributions of water, which is kind of in large part driven by the details of these kind of exchanges between these different reservoirs, as well as if we think about clouds, the details of kind of the particle size distributions. All of these things kind of make the water cycle a key player in driving planetary climate. And one thing that we can kind of emphasize is that the connection between our clouds and surface water reservoir, unlike these other connections, the precipitation transferring water from cloud to surface isn't a reversible process, and kind of this makes it a key link in driving the behavior of this water cycle that's so important for planetary climate. And also we know, like, as humans, we kind of care about the details of what precipitation is doing for weather. Oops, didn't advance. So we kind of want to understand how clouds make precipitation or make rain if we're just thinking about our liquid phase for all these climate and weather consequences. But actually modeling and understanding how clouds make rain is kind of complicated for a diversity of reasons, spanning from kind of gaps in process-based understanding from a kind of more physics or scientific perspective. We also have a lot of really complicated math because we have a lot of nonlinear processes that are all coupled together, and we're dealing with kind of not only the water cycle, but also interactions with radiation and chemistry and aerosols and dynamics. And we also have dependencies on time and length scales that vary by many orders of magnitude, which kind of make numerically modeling this problem hard. And so kind of amidst all that complexity here, I want to specifically focus on cloud rainmaking from kind of the liquid drop perspective. And the idea is we kind of want to look at simplified microphysical representations of how clouds make rain, because this is necessary both kind of conceptually understand cloud evolution, and also if we want to parameterize the microphysics to put into larger scale models. And in this talk, I'll kind of basically only be focusing on liquid drops. Of course, we also can have ice particles making up clouds as well, but this is just a picture of a bunch of kind of frozen, collected in situ ice particles. And maybe if we just kind of compare them to the cloud drops, you can see maybe this is a second problem to think about after we think about the liquid. Okay, so this talk is kind of divided into two parts, and the first is kind of going to be focused on generalized planetary atmospheres, and the second specifically on modern Earth. And I'll just acknowledge here that this work which is part of my PhD thesis. That was all done with my advisor, Robin Wordsworth. So to start, I want to think about clouds and kind of generalized planetary atmospheres, and this is kind of relevant for solar system bodies, both at present and through time, and also for exoplanets, or planets outside the solar system, which we're now in the era of being able to actually characterize and make observations about. And clouds, like on modern Earth, kind of play a really big role in how we interpret observations coming from these bodies, and also have a really important role for setting planetary climate. And so, of course, we know clouds on Earth are complicated, but at least there we have kind of a lot of observations that can help guide our thinking. When we start branching out to other planets, we have a lot fewer or no observations. And so the idea of this work is to kind of try to use something that's simple about cloud evolution and then see what that can tell us about some of these more complicated cloud processes. So the idea of this work, which is kind of takes inspiration from a great paper of Ralph Lorenz's about Titan raindrops from 1993, is to kind of exploit that the physics of what kind of liquid drops or raindrops do after they leave the cloud and stop growing. And by leaving the cloud, I just mean they enter subsaturated air. They're actually pretty simple. They're just kind of falling and evaporating. And so we want to use the simplicity of these below cloud raindrops and kind of just ignore all of the details of what's happening inside the cloud and look at what that can tell us about cloud evolution. And when we kind of focus on an individual raindrop, we can kind of conceptualize the kind of two fates it can have. It can either evaporate or it can precipitate, by which I just mean it can transport at least some of its mass to the surface or some kind of critical vertical level. And so kind of the background that kind of sets up this work is that we need to calculate kind of three basic raindrop characteristics as a function of size, and that's shape, terminal velocity, and evaporation rate under general planetary conditions. And then we use these characteristics to model the time evolution of raindrops below a cloud. And basically, a driving conclusion of this work is that there's kind of strong size feedbacks that govern raindrops' fates toward evaporation or precipitation that can help us kind of frame this complicated problem of drop growth. And so here I'll just show one example. This is from modern Earth conditions. We have on the x-axis kind of height, so the top is cloud-based, the bottom is the surface, and on the y-axis we have drop radius in microns on a log scale, and we have a bunch of different color initial size drops exiting the cloud, and we can kind of evolve time forward and see what happens. And we can basically see there's really strong feedbacks of size and how these drops fall. And so the bigger drops kind of basically make it to the surface at about the same size as they started, and the smaller drops completely evaporate. And this is from the combined dependencies of evaporation and falling falling velocity on drop size.
Sorry, how did you compute that figure? Like using a model? Or?
Yeah, so basically we have, we calculate the rate of droplet, we calculate droplet size as a function of time, and we also track droplet vertical position as a function of time.
Okay.
And we also track droplet temperature as a function of time.
With some kind of like cloud microphysics, like?
It's all kind of like simple physics equations.
Okay.
So we kind of assume a background atmospheric profile. You can make different assumptions. Here I think we just have kind of a well-mixed water layer starting from kind of assumed surface conditions and then going until we hit 100% relative humidity, which is cloud-based. Yeah.
I don't understand why you've omitted droplet breakup, right? There's this whole idea of an equilibrium size distribution, which is, you know, collisions and hydrodynamic instabilities and all that. It seems like that's a big part of what raindrops do.
That is coming.
Okay.
Yeah, so we also look at droplet breakup as a constraint on drop size. Okay. So basically, schematically, what we can see is there's a strong positive feedback on raindrop evaporation as raindrops grow smaller. So if we kind of look at the fraction of mass evaporated between the base of the cloud and some vertical distance below it, we can see as a function of size upon exiting the cloud, we have a fairly sharp transition from where the raindrop is all evaporated until it goes to almost none of it being evaporated. And we'll kind of look at this mathematically in a bit. Okay. And so from this, we can kind of define a critical size. Here I call it R min. And the cloud needs to grow raindrops larger than this critical size in order to move water from the cloud to the surface. And so microphysically, we can start to think about precipitation efficiency, or what fraction of mass the cloud is able to convert into precipitation. Microphysically, this is kind of set from the fraction of mass that's in drops above this threshold at the cloud edge. Additionally, we can put other kind of constraints on raindrop size, one of them being that raindrops become unstable above a certain size. Here I've called this our max. Here we're putting this constraint just from the stability of a single drop. The stability of drops interacting with each other is a little bit smaller, but kind of for the purposes of what we're trying to do here, in order of magnitude, we kind of ignore that tighter constraint and just say, when do liquid drops become unstable as a maximum drop size?
Do you expect the Rmin to change as the subcloud layer is moistened by evaporation?
Yes.
Okay.
And I'll show some differences in that in a bit. And also because at least liquid water homogeneously nucleates at very, very high supersaturations, we can also say that drops are going to start from some non-zero size from a CCN. That's much below this instability threshold. And we can use this threshold R min for clouds to kind of reach, for a raindrop to reach a given surface or vertical layer below the cloud, to kind of bound the sizes of raindrops that are able to reach a given vertical distance below the cloud, kind of completely independently of growth mechanisms. And what we kind of want to know is how do these different kind of values of radius values of interest vary across different planetary environments. And so what we find is that the size range of, here we're thinking just about kind of terrestrial bodies, so the size range of surface-reaching raindrops is fairly narrow and also pretty similar across broad planetary conditions. So here I'm going to show varying surface pressures, surface gravities, and surface temperatures. And also on the y-axis we had our raindrop size when kind of exiting the cloud in millimeters. This is on a log scale spanning 6 orders of magnitude. And the first thing we can do is kind of plot this upper bound on stability, which we can see is kind of consistent across, fairly similar across these variable conditions. And as kind of Marcus was mentioning, a kind of key dependency is how large of a distance do you have between the cloud and the surface. Is going to change based on what you assume the surface relative humidity to be. So we calculate this bound here for visualization purposes for 3 different surface relative humidities.
So the basic assumption is that surface temperature doesn't affect the cloud, like the depth. Sorry, the depth of the mixed layer.
Yeah, so we basically either choose conditions at where the cloud reaches, so basically where relative humidity is 100%, which we kind of say is the cloud base.
Yeah.
Or we choose conditions at the surface.
Oh.
We assume moist adiabat and assume well-mixed constituents, and then either integrate up or down to set the profile. So the profile isn't interacting with the behavior of the evaporation.
And so the surface humidity is not what you're using for your evaporation. It's just to set the lower.
Yeah. So this is setting the profile of how much water vapor there is as you move from the surface to the cloud base. And so because as we set, so this is showing the bound, the lower bound for 75% surface relative humidity, and the shaded region between is kind of what the range of size range of surface reaching raindrop is under these conditions. We can also change the surface relative humidity, so I can add 50%, and we can see this gives us a tighter bound. This is mostly just driven by shrinking the distance between the cloud base and the surface. And finally, I can press a button on my computer to advance the slides. It's not working. Finally, we can also add 25% relative humidity, and we can see we get an even stricter bound. And so we can see across all of these planetary conditions that we have about an order of magnitude for raindrop size bound, and these bounds are largely kind of overlapping across all of these conditions. And kind of put this in perspective, we can add kind of a sketch of where we expect our cloud condensation nuclei sizes to be. And we can kind of see we need to have significant growth from these sizes in order to get drops that can reach the surface.
What makes the non-monotonic behavior in the surface pressure? It's kind of interesting.
Yeah. So surface pressure, I guess I'll say we didn't really expect these to look similar. It's actually expect them to look quite different. But yeah, there's kind of a few competing effects from the surface pressure that give you this non-monotonic behavior. We could talk more offline about that if you want. But that's just kind of the outcome. We have a bunch of coupled differential equations, so it's not that surprising that we see some nonlinearities. Okay. And so the next thing we can do is kind of, here I just had a fixed surface, but we can also just look at how raindrops can transport mass downwards just as a function of vertical distance. And what we see is that kind of across planetary conditions, that raindrops of the same size transport water mass similarly. And so here we're just going to look at a few specific examples, but in the paper we kind of show this in more detail. And so now I have flipped my initial drop size in millimeters to be on the x-axis, and my y-axis is showing my distance from the cloud. This is in units of scale height in a log scale. You can put this in physical units like meters, and it looks pretty similar, just a little bit different relationships. And we can kind of, again, add our cloud condensation nuclei sizes on. And just to give context, I'll show kind of the lower bounds and upper bounds as a function of distance below the cloud, specifically for Earth. And so we can see that as the raindrop kind of continues moving down from the cloud, the bound on sizes that can transport mass to that distance becomes tighter. And that's basically just coming from the lower bound shrinking. And I can add these lower and upper bounds for a few different planets. So here I'm showing Earth which I just showed, a hypothetical early Mars, Jupiter, Saturn, and then an exoplanet. It's a mini Neptune, K218b, which people have claimed to detect liquid water clouds on. And so basically what we can see is that these lower bounds and upper bounds are not spanning, are pretty tightly constrained across all of these planets. And we see that basically raindrop size is kind of the predominant determiner of how this water mass is being transported. And again, we can see this question of growth. Even to transport a very small distance below the cloud, we still need to have an order of magnitude or two of growth. And we need more growth to get farther down. Okay. Next, we kind of want to think about what's driving this behavior. And what I want to show is that actually we can understand basically all of these results in the context of just looking at a non-dimensional number. And that's going to be the ratio of the time to fall over some distance L to the time to evaporate given by this tau evap. And kind of, we can say that in order to get rain to our disk surface, or whatever distance L we're considering below the cloud, we need to have our falling time be faster than our evaporation time, or we need this ratio to be less than 1. And basically what we would kind of like naively expect, and we actually find that computationally works out, is that we can approximate this threshold, this Raman threshold, to actually have a drop reach the surface. We can calculate this by just setting this ratio equal to 1. And we can also calculate the fraction of drop mass that's evaporated over this distance as just the minimum of this ratio in 1, because we can't evaporate more mass than we start with. Yeah, and we kind of show in the paper that this kind of quantitatively works out. And so we can kind of look, because this is just a fairly simple expression, it's getting cut off, but this is just the same fall time to evaporation time ratio. We can look at kind of the dependencies, and we can see that for smaller drops, so drops kind of in the Stokes regime, that this ratio kind of depends on radius to the -4. So we have a really strong nonlinear dependence on size, and that's kind of driving a lot of these behaviors. And basically, I'll just quickly show that I can reproduce all of these results I was showing previously that are from coupled ODEs with just using this ratio. So if we're looking at these minimum sizes to reach the surface, now I just show in the little lambda symbols, because that's what our non-dimensional number is, that we can basically match all of the lines from our ODEs with just using this ratio. And I can do the same thing from our minimum size threshold as a function of distance from the cloud. We can go through all these different planets. So here's Earth, Mars, Jupiter, Saturn, and K218b, which is that exoplanet. And so basically the idea is that we can kind of understand a lot of these more complex behaviors just by looking at this much more simple ratio. Cool. So to kind of wrap up this section, we kind of looked at how the simplicity of raindrops can help us frame liquid cloud evolution. And across broad planetary conditions, I showed that a raindrop size is kind of what determines its fate after leaving its cloud. Only a small range of possible drop sizes can reach the planetary surface. Raindrops of the same size transport condensable mass similarly. We need significant growth of liquid drops to get rain. And also that we can kind of capture the behavior of these falling raindrops with a non-dimensional number. Cool. Okay. So with that, I'll kind of lead into the next part, which is how do we go from thinking about these generalized planetary atmospheres to modern Earth. And this is kind of motivated by the next question, which is obviously how do we kind of grow the drop from these CCNs into this threshold size? And at least on Earth, on modern Earth, we know that drop growth to these sizes kind of requires us in liquid only clouds or warm clouds to have interactions with other drops. And there's kind of this key process. We kind of can grow by condensation, but at some point, the dominant growth process that takes us to these surface reaching sizes is this process of coagulation, which is just the collision and subsequent coalescence of nearby drops. And this, I think, kind of I was kind of looking for, simplified representations of coagulation, and kind of an obvious place to start is how it's parameterized in large scale models. And so this kind of led me to this next part, which is thinking about how global climate models have this longstanding and widespread bias in that they have too frequent, too light rain, and how this might be related. Yeah.
Not everyone believes that. I mean, my impression is that comes from people looking at CloudSat, which is looking at clouds from above with a very not very sensitive radar. And if you look from below, they're always drizzling. So I don't think there is such a bias. I think everyone's looking at the wrong instrument.
Okay.
I'm not the only person saying that. It's not
That's
my idea.
Yeah. Yeah, maybe I can discuss that in a second. Yeah. So yeah, and what this work is looking at is how kind of a paradigm of how this coagulation process is parameterized in the kind of unphysical way could be potentially tied to this bias, and kind of regardless is unphysical. And how we kind of parameterize this coagulation process in these global models is important because it kind of is initiating warm rain and also kind of shaping cloud radiative properties, which has important consequences for planetary albedo. And so kind of to look at this problem, I will show some CloudSat data. And here we have radar reflectivity on the x-axis, kind of characterizing, kind of divided schematically into three regimes of non-precipitating, drizzling, and raining. And then I'll show PDF on the y-axis. And here we have in the pink data from CloudSat at two different spatial scales to kind of compare to different spatial scales of models. And here's kind of what the equivalent radar reflectivity in the models looks like. So I guess regardless of the question of the exact framing of this drizzle problem, I think something that's we can fairly confidently say is that a lot of these models basically don't make clouds that don't rain at all.
Correctly so.
That's correctly so.
So the drizzle in the cloud, you're saying, is okay.
I'm not saying everyone's cloud parameterizations are good or everyone's drizzle parameterizations are good. I'm just saying this notion. I mean, Momenstadt wrote this paper recently, and so we roped him into this paper to look at the radar simulator when you're looking from below, and he's like, oh, I see. I was looking at using the wrong instrument. And anyway, so there's this wide, and Graham Stevens has been going around for years saying this, and it's just based on a bad instrument to look. If you want to look at how it's raining from clouds, it's better to look from under the clouds than to look from orbit.
But the sensitivity, what is the sensitivity that you need to detect sort of below cloud?
I mean, what is drizzle? I mean, it's like, so you can get into, so depending on what your sensitivity is, you see more stuff, obviously, right? But, so, I mean, CloudSat also has problems with ground clutter, right? They can't even use the reflectivity. They have to use the attenuation when they get near the surface. So, I don't know. What was your question?
So if once you're out of the cloud and you're standing on the surface, is there a drizzle bias or no bias?
So
I know you mostly think about clouds, but
No, I think about precipitation a lot,
Okay.
and it's like, do some models drizzle too much? Maybe they do. I don't know.
Does our model?
But well, the new model is. I mean, so have I looked at that? No, but I do not have any reason to believe that all these people who think there's a drizzle problem, there's a bias. I don't believe that their observational target is the correct target. I think it's mistaken, and it gives everyone this bad impression. Which is not to say people shouldn't think about drizzle and all that kind of thing. I'm not saying it's a worthless problem. I think it's a very worthwhile problem. But just the idea that CloudSat is correct, telling us how much stratocumulus clouds, for instance, are drizzling, I think is mistaken. I mean, because seriously, you look underneath and you see them drizzling all the time.
I think that's I guess one question I would ask is if you're looking at the radar reflectivity as just kind of characterizing kind of top of cloud, like some property of the size distribution, is that offensive?
I'm not offended. I'm just telling you that I just think people have a mistaken impression by looking at it.
So the CloudSat you should take with a grain of salt.
If you're looking at surface precipitation and light
Okay.
drizzle, for sure. I mean, or if you're looking at heavy rain, then you have attenuation problems.
But if you just want to know if you're generating larger drops within the cloud, not necessarily whether or not they're making it to the surface.
Sure, you should be able to see within the cloud.
Yes.
As long as that cloud isn't very close to the surface.
Yes.
I mean, you're going. It attenuates at some point. I mean, at some optical depth, class attenuates in terms of looking at rain underneath the cloud.
Yeah.
So, are you using the CloudSat simulator to?
So
look at
the edge is cut off. This is adopted from work by Jing et al. 2017. So I didn't do this processing. This is just kind of a motivating factor. And I guess I would say even if the clouds, regardless of what's happening at the surface, the evolution of the size distribution within the cloud towards larger, towards having larger kind of drops that potentially could be capable of reaching the surface. Maybe drizzling and raining is not quite the right way to frame this. But having these kind of larger drops, which the radar reflectivity is sensitive to, CloudSat is seeing that most clouds are kind of dominated by really much smaller size distributions without these kind of larger particles in them. Whereas if we translate what the models are predicting with a simulator back to what CloudSat is doing kind of across spatial scales, or spatial resolutions of the model, we see that we have this like complete dearth of non-precipitating clouds. So the clouds are basically always, the clouds in the models are basically always making particles that are big enough to potentially reach the surface. And the process of this transition in size or in radar reflectivity is driven by this, by coagulation. And so kind of the larger motivation of this is could the way that coagulation is traditionally parameterized in these global models drive to rapid rain initiation, but you could also look at this work as there's kind of unphysical assumptions in how these models are representing this process. Okay, so to kind of see what are the global models doing, we kind of take CMIP6, the most recent global model, global model intercomparison, and we kind of catalog how they're representing coagulation. And basically what we find is even though there's lots of like details that are different, these parameterizations all share the same fundamental structural assumptions. And it's basically that we have kind of two size categories of drops. And one is kind of small drops that we can call cloud drops. The other is kind of big drops that we can call raindrops. And how coagulation is represented once we've kind of reduced our kind of continuous range of drop sizes into two categories, we have a lot simpler coagulation process. So we can transfer mass into the bigger raindrops via two processes. The first, which is kind of the perennial problem, is called autoconversion, and this is when you have cloud drops in this cloud drop category interacting to form raindrops. And we have a second process called accretion, and this is when you have drops interacting in this small category and big category to transfer more mass into the big category. And these parameterizations consistently make two assumptions. The first is that the width of the drop size distribution is not important to the evolution of the coagulation. And by drop size distribution width, I just mean here we have schematically two clouds that are the same kind of mass of liquid water and the same number of droplets, but the distribution of sizes is quite different. So we could have kind of all the drops be the same size in a narrow distribution, or we could have a mix of particle sizes in a kind of broader distribution. Yeah.
I don't understand how you write this, the word all, because I mean, there are a bunch of drizzle parameterizations out there that depend on the width of the
CMIP6.
Yeah, I mean, Seifert, you're saying no one is using Seifert's autoconversion scheme, or no one's using the Lee autoconversion?
So when they use it, they fix this parameter. They don't vary it.
Well, I know that I don't know what Cam is using these days, but they use a diagnostic. I don't believe what Hugh is using, but he has a diagnostic dispersion relationship, which I think is baloney. But it's
not fed back into the how autoconversion.
Well, then they're doing it wrong, because it should. If they're using Seifert's autoconversion, it's right there.
But that's not what the CAM version that's being contributed to CMIP6 as the this is our.
I'm amazed no one is doing that. I mean, we are doing it, but we're not in CMIP6.
Yeah,
it's unfortunate. We're not.
So
I know that.
So E21 did not do this.
4 years, how could we possibly do that yet? What's that?
So E21 is like what the slide says, but E3 will have this size thing.
Well, I use Seifert's expressions because I think they're better, and I assume a fixed dispersion, because I don't believe that there's a robust relationship from what I've seen.
I think that's questionable, but I think that also does have a really big effect on how the growth processes evolve.
So anyway, in our model, this is not true, but what is true is that we do not have a systematic change in the breadth of the distribution.
Yeah. So some of the models have a term, but it's not interactive. So it's basically just a parameter. And so you're not accounting for this dependence if it's just a fixed parameter.
It depends on their choices, but anyway, they're all available.
And this is also just what people have published and kind of documented. So what's actually in the models could be something completely different. Yes, and the next step is to actually talk to the modelers to make sure that what they're publishing as what they're doing is.
So Seifert's 3-modal scheme hasn't gotten in the ECM CMIP6?
No. So again, a lot of these models can have different flags for if I'm just running the name list if I'm just running the model as a user, there's maybe something in the name list or buried somewhere that I can turn a flag that it changes what scheme. And the Seifert's embedding scheme kind of corrects these problems. But that's not what's actually in the operational models if you look at what is being put out there in CMIP6 and being analyzed.
Curiously.
Yeah. Which is kind of crazy, considering this is kind of been pointed out as problems since basically it was developed.
It's expensive, right? I mean, or no?
No, it's just a different.
No.
It's just a one line of math. It's people for some reason like Krunov and Kogan. I don't understand that at all. But
so
it's very simple.
Why didn't we just have that one line and see what difference it made to our rainfall distribution?
I don't believe Krunov and Kogan should be even used. I don't even know why people consider it. But we have it as an option.
Okay.
It's available there and in our code. E3.
Oh, okay.
I wouldn't recommend it.
Yeah, so part of this might be highlighting like what's actually in these models is not what's kind of regarded by the microphysics community as like really robust parameterization. But that's what's in these operational models, and that's what's kind of being used. And this does have significant implications, even regardless of the drizzle bias question of cloud coverage and cloud albedo, especially as we move out of the regime of satellite observations to constrain like shortwave cloud effects. Okay, so this first assumption is that the width of the size distribution doesn't matter. The second assumption is that there isn't any dependence on cloud aging. And so you can kind of see why this might be something physically we want to put in, just from this kind of schematic example. So as we kind of go through time, we only have 2 size bins. But we can kind of imagine in the initial stages of growth where we haven't really had any coagulation, we've just had condensation, we have quite small drops when they interact. They just produce more small drops. And as we go through time, the kind of base size of drops that are interacting in this kind of cloud or small drop category grow bigger, and eventually we can produce this larger drops in the rain category. Instead, what the models are assuming is that we can kind of basically just average over all of these effects. And so it's always kind of the same result. It doesn't matter that we can kind of expect this with evolution. Basically, if 2 cloud drops are going to interact, they're always going to have the same capacity to produce these larger drops.
What is the time scale of this process? Like minute or seconds or?
So that varies a lot depending on, for example, how much liquid water is present, how many drops you have, average drop size, and also the distribution width.
I see. Because, in any case, the GCM's, each time step is like 30 minutes or it could be like 15 minutes, but, that is like a shortest time scale we can capture. So
yeah,
if that is like this process is much shorter than that, then there is no way to.
Yeah. So it can be, but it can also be much longer, I guess, is kind of and it doesn't kind of guard against this much longer. Instead, we just kind of really rapidly produce rain. Cool. And so kind of the setup of this study is that we just want to look at what these CMIP6 assumptions look like versus kind of a size resolved model in a really simple framework. So we have a spatial 0D model, and we only have the operation of this collision coalescence process. And we also have idealized initial conditions where we just take a gamma distribution and specify it from the drop mass concentration, the mean mass radius of the drops, and also how wide the distribution is, which we characterize by the distribution relative dispersion, or sigma naught. And then we kind of have 2 types of models. The first that we kind of use as a benchmark is a bin model that I've built. And then the second is a bunch of different models that we call bulk models that are based on these CMIP6 structural assumptions and tuned to match the results of this specific bin model. And we basically, so as I said, there's a lot of different ways beyond this shared structural framework that the CMIP6 parameterizations work, and so we kind of change different assumptions. So I think here I have 8 different bulk models. And so what we do is kind of just compare the amount of time it takes to initiate rain across broad initial conditions informed kind of by in situ observations of warm clouds in these CMIP6 based models and also in our kind of benchmark model. And here to kind of be able to plot things visually, rescaled, basically removed the dependence of the amount of water that's present in these simulations based on math. And so basically you can just scale this time by, depending on, you can just scale it based on how much water you have. Okay, and so for the bin model, we have specified how broad this distribution is, and so I'm going to show results in terms of the spectral dispersion, and so as you go from blue to yellow, you're getting from narrow to broad distributions. And, this x-axis is showing our initial condition for the average mass drop radius. And so basically what we can see is as we move towards smaller initial average drop sizes, the dependence of how fast we form rain on how wide the distribution is starts to drastically increase. And we can also look at all of these different bulk models that are built following the CMIP6 structural assumptions. And so these are in just different colors here. And here I just have colored the range. This is for, I think, 10,000 different initial conditions each, and the range of rain initiation values as those vary. And basically what we can see is that we, of course, don't capture this dependence on how wide the distribution is because we have this, that isn't something that the CMIP6 parameterizations have access to. And so because of that, we see fairly narrow ranges of spread in how long it takes to make to initiate rain once we've removed the dependence on the amount of water present as a function of the initial mean mass radius. And so kind of collectively, you could say these can cover the spread of kind of our benchmark model, but individually, they're all only capturing a small slice. And so basically, what we can see is that the kind of, based on the assumptions that these models are making, we kind of have a choice between representing most of the initial conditions well and not representing kind of this narrow small drop regime. And so that's kind of this cluster of schemes. Or we can try to represent these kind of narrow distribution, small drop initial conditions, and then kind of do a bad job of representing most of the initial conditions. And so kind of the cost of representing most of these initial conditions well is the too rapid initiation of rain for the narrow distribution, small drop initial conditions. So basically, if we choose these this type of parameterization, it's never taking us all that long to make rain. We're missing out on this kind of persistence here. And so the next question is to kind of ask, well, is this kind of parameter regime, this problem parameter regime for the CMIP6 parameterizations a problem? Like, does this actually occur in the real world? And so we look at in situ observations of drop size distributions to kind of try to answer this question. Here we just have analyzed one field campaign from the Northern Atlantic ENA site. And so basically what we find here, I'm just showing now the spectral dispersion. This isn't conditioned on being the initial condition anymore because we don't know that in observations. And the mean mass radius and the 2D PDF in log space. And so in yellow is like what's really frequently occurring. And so what we can see is basically about like 50% of the observations are kind of in this regime of kind of narrow distributions with small drops in this campaign. And so this is about 40,000 observations. And so kind of clearly this needs to be investigated over kind of more field campaigns, but it does seem to indicate, at least in this campaign, this problem regime where the kind of CMIP6 assumptions break down is fairly common in observational clouds.
So I'm curious, what you filtered out somehow? You got rid of the collection mode, because we're always talking about the dispersion of the condensation.
Oh, sorry, I forgot to mention. So we use this holodeck instrument, and this can measure simultaneously all the drops from about 5 microns in radius to about 1 millimeter. And so this is the width of the distribution, including all of those larger drops.
But that's not what goes into the auto conversion scheme, right? That should be the dispersion of the condensation mode.
Yeah, but this is like limiting. Drops. So this is like the limiting.
So this would be even wider than if you only consider.
If I just took like the me scattering instrument and just took drops up to like 25 microns in radius. So this is kind of like, the best. You would expect larger, broader distributions, and you can kind of see that as you get to these larger drop sizes, you tend to have much broader distributions. Because there are perceptible sized particles sometimes in here. Okay. And so kind of one takeaway, maybe independent of this drizzle bias, is that these parameterizations that are in the actual operational CMIP6 models seem to kind of be using parameterizations that physically break down in observationally common regimes. And this is also, the behavior that comes out of this is also consistent with this potentially shared too frequent rain bias. And the last part of this presentation, which I'll just kind of skim very briefly because I'm almost out of time. The question is, like, if we kind of make parameterizations that kind of account for these assumptions, not necessarily, not adding more variables, just making better assumptions. Can we kind of improve warm rain initiation timing? And basically, we try 3 different kind of approaches. One of them kind of being basically Seifert and Bang, but kind of retuned to this bin model. And then kind of 2 newer approaches. And I'm just going to skip all of these. We basically find that we can do a lot better than the CMIP models. And so actually accounting for distribution width and aging effects does seem to improve rain initiation timing. And the 2 kind of newer schemes that I didn't have time to go over don't use auto conversion at all, and so kind of thinking about ways to move past using this kind of flawed conceptual process. Cool. And with that, I guess I'll kind of conclude and can take any additional questions. So, thanks.
Questions during the talk?
The falling time that he had in the first part, isn't there a dependence on vertical motion?
Yeah. So I didn't have time to kind of go into it there, but we kind of do look at this in the paper. I shouldn't have exited out of the slideshow. Okay. So we kind of also look at this as a function of vertical velocity. If we want to get any of those like scaling arguments, we have to set vertical velocity to 0. But
I'm wondering to what extent your surface pressure dependence includes some vertical velocity dependence.
Yeah. So we kind of thought about trying to like include something like that. How to kind of include something like that, and we ultimately just kind of left it as an open parameter because it's yeah, really hard to try to characterize that. But the basic effect is like if you get extremely strong downdrafts much, much faster than all of the drop's terminal velocities, then you'll kind of lose dependence on these kind of drop physics. And as you get updrafts, it kind of makes this dependence even stronger because the smaller drops aren't even kind of falling downwards. So kind of a threshold size to even start falling.
All right.
Yeah, thanks for that.
Let's see the other parameterizations if you have time.
Sure.
So one is this time scale, the aging.
Mm-hmm.